I'm Elizabeth, and these are my teammates Luisa, Scott, and Kate, and we are here today to present our senior design project, which focuses on analyzing the economic and technological feasibility of designing a plant using a proprietary reactor in order to convert carbon dioxide to transportation fuels using sunlight. So let's take a look at the current state of the energy market. In 2013, global petroleum demand was about 90.4 million barrels per day, and this number is expected to increase by over 1 million barrels per day in both 2014 and 2015. We obtain this oil by drilling, a process which is both expensive as well as filthy. Unfortunately, oil still comprises our most commonly consumed form of energy at 37% of total energy consumed. Therefore, a lot of research has been done in order to identify renewable sources of energy. One of these areas is solar power, because of the massive amount of energy that the sun delivers to the Earth's surface. In fact, every 70 minutes, global energy demand is met by the sun. However, success has only been found in converting solar power to electricity, and this does not meet the growing demand for transportation fuels. As it stands now, our transportation system predominantly runs on liquid fuels, and it will never be able to be fully powered by electricity alone. Therefore, there is still a large need to identify renewable sources of energy to produce these fuels, and that's where we come in. We will use a CR5, or counter-rotating ring receiver reactor recuperator, that is currently being developed at Sandia National Labs by Dr. Richard Diver. This reactor uses concentrated solar power in order to drive highly endothermic reverse redox reactions. We will use this in combination with water-gas shift and Fischer-Tropsch reactions in order to produce transportation fuels. Let's take a closer look at the CR5. Each reactor is attached to a parabolic mirror dish that has an area of about 88 meters squared. The rings of the CR5 are made out of iron oxide. As you can see, sunlight is concentrated on the top portion of the CR5, known as the reduction chamber, which then heats up to temperatures of about 2300 degrees Kelvin. Here, oxygen is stripped away from the iron oxide rings. The rings then continue to rotate towards the oxidation chamber, which runs at about 600 degrees Kelvin. Here, carbon dioxide is fed in, and the oxygen-depleted iron oxide rings can steal an oxygen away from the carbon dioxide, producing carbon monoxide, which will be used later on in the process. It's also important to note that both chambers of the CR5 run at subatmospheric pressure of 0.2 atmospheres. As you can see on the bottom right-hand side of the slide, the rings of the CR5 are counter-rotating, which allows this device to be more energy efficient during heat transfer. Now I'll pass it off to Luisa to talk about our process.
This is the overall process overview of our plant. We start off with the carbon dioxide going to each of the 150 CR5 units to produce carbon monoxide and oxygen. The carbon monoxide is then split and travels into the water-gas shift, where it reacts with water to produce hydrogen gas. The hydrogen gas then reacts with the remaining carbon monoxide from the CR5 unit in the Fischer-Tropsch reactor to produce transportation fuels. However, this is a simple model and does not provide us with the depth to assess the technical feasibility. So we use a program called Aspen, commonly used in the Chemical Engineering Society. In Aspen we can build a process model that simulates plant conditions. We insert in the chemical components, the temperature and pressure at each stage, as well as the chemical reactions occurring in each block. And this will give us the thermodynamic conditions, as well as the composition in each intermediate stream, as well as allowing us to produce a sensitivity analysis to allow us to maximize the production of our product. This is the overall design process. We started with the overall plant design that I showed before, and we used some basic calculations to plug in the known values into Aspen. We iterated that until we maximized the production of our final product. After the Aspen simulation was done, we then calculated the equipment sizing. Then we evaluated the economic feasibility of our overall plant. This is what an Aspen flow diagram looks like. This is the CR5 unit that Elizabeth has described. This is the water-gas shift, and this is the Fischer-Tropsch. Both the water-gas shift and the Fischer-Tropsch reactors are fixed bed catalytic reactors. The water gas shift uses a conventional catalyst of iron oxide to produce from carbon monoxide and water, carbon dioxide and hydrogen gas. The Fischer-Tropsch reactor needs a specialty catalyst, and we've chosen cobalt. I will explain why we chose cobalt. So the Fischer-Tropsch reaction converts carbon monoxide and hydrogen gas into different lengths hydrocarbon and carbon dioxide and water. This reaction occurs on the surface of the catalyst. Different catalysts will dictate what the prominent hydrocarbon will be. Hence, we use the Anderson-Schultz-Flory distribution that describes what the Fischer-Tropsch catalyst will produce. The cobalt produces mostly octane, which is what we're trying to optimize. Other Fischer-Tropsch catalysts will also produce octane. However, we've chosen cobalt because it's a trade-off between production and pricing. Cobalt, of all those catalysts, was the only one with a reasonable price. This is what our final liquid product stream looks like. As you can see, it's mostly liquid transportation fuels. And out of this liquid transportation fuels, we have 5% naphtha, 21% gasoline, 21% diesel, and the rest heavy ends. Now I'll pass it off to Scott to talk about plant operations.
Thanks, Luisa. So in deciding the major operations of our plant, there's a number of important considerations. So of course the first one is that our CR5s are dependent upon solar availability. So they're dependent upon solar flux and as such can only run during daylight hours. Now this raises the question of what to do with the rest of the plant. So we had two major alternatives. We can run the rest of the plant continuously, storing extra CR5 output during the day and depleting it throughout the night, or we can store, and that's considered the storage option, or we can run semi-continuously, whereby we start and shut down the plant every day. And so, theoretically possible, the continuous operation is very difficult due to the large number of storage tanks created. And as you can see, these types of storage tanks, we would need an additional 111 to do this continuous operation, which while economically feasible, may not be technologically feasible. And so we wanted to next look at a number of energy requirements throughout the plant. So we were able to do heat integration to minimize, to reduce steam, as well as utilize cooling water throughout the plant. However, we still have a number of electrical requirements. So our overall electrical requirement is 1,300 to 1,500 megawatts, which is equivalent to some of the largest power plants currently on the grid. And obviously this is too big for our plant. So we wanted to look at why this is done. And this is primarily driven by our compressors. So we wanted to look at a number of power recovery schemes to minimize our electrical demand. And so what shown again here is our Aspen flow diagram. And so inside the Fischer-Tropsch section, we have this gas purge stream. This gas purge stream has a number of components in it that we can burn to create electricity. So in this stream, we have hydrogen, carbon dioxide, carbon monoxide, and light end hydrocarbons, all of which we can combust to obtain energy back. Obviously, we also wanted to continue looking for other power recovery schemes. So coming out of the CR5, we have a hot oxygen product at 2300 Kelvin, and so this has a high energy potential. We wanted to be able to generate heat and thus electricity from this. So since the actual CR5 pressure is so low, the outcoming O2 is only at atmospheric pressure. We thus run it through a heat exchanger where we can create high pressure steam, which then runs a turbine. Overall, this has a reduced demand of around 1 gigawatt. So we only have a residual requirement of 300 megawatts, which can be easily purchased from the grid. Now I'll pass it off to Kate for an economic evaluation.
Thanks, Scott. So my teammates have told you why this scheme of converting solar power to transportation fuels is technologically feasible. I'm going to tell you why it's also economically attractive. So we'll start off by looking at the capital costs, which are a total of $1.5 billion at the onset of the plan. So as you can see, the CR5 reactor cost is really not the driver of this capital cost, as you can see up here. However, the Fischer-Tropsch catalyst and the compressors and the piping are really what drive this. So looking at the Fischer-Tropsch catalyst, As Luisa mentioned earlier, there's a trade-off between price and quality of the product. So further research could be done to identify a Fischer-Tropsch catalyst that could potentially have a lower quality output, but would be cheaper and could make it a more economically attractive scheme. Also the compressors. So we mentioned earlier that the CR5s are running at sub-atmospheric pressures, and if there were further research to allow for atmospheric operation, the compressor price would be significantly decreased. Now moving on to annual operating costs, which are $450 million annually. You can see that a significant portion of that is consumed by the 62% that's attributable to the daily startup and shutdown costs associated with shutting down and starting up the Fischer-Tropsch and water gas shift catalyst. So this indicates to us that if we were to find a way to feasibly store the outputs from the CR5s to allow for continuous operation of these other reactor schemes, this would be very attractive. So the plant itself has three main drivers of revenue. The first, of course, being the sales of our fuel to refineries. So we price the fuel at 2 times the market price of crude oil, and this is due to the fact that the impurities found in crude oil are not present in our Fischer-Tropsch fuels. Additionally, we'll be receiving fuel subsidies for the production of renewable energy, and we'll be receiving carbon credits for the reduction of carbon dioxide, which is a greenhouse gas from the atmosphere. So of course, all of these variables are very subject to assumptions. So we ran a sensitivity analysis around 6 of the key variables, running a best, base, and worst case scenario. This was to identify what the main drivers of the economic attractiveness was and to see if it was actually feasible. So by doing a net present value evaluation on the 3 cases, we identified that this does have a positive net present value for the best and base case scenario. And the worst case, as you can see, is negative. So what this indicates to us is that the scheme of converting solar power, solar energy to transportation fuels is both technologically and economically feasible. Current research, as we mentioned earlier, is really focused on the conversion of solar to electricity. But as we all are aware, our transportation infrastructure is really dependent on transportation fuels still. So we think that this is a very viable process to further investigate. We do identify, though, that there are several areas of further research that are necessary or could better improve our outcomes. So the first being the ability to operate the CR5s at atmospheric rather than sub-atmospheric conditions. Also, the ability to store that CR5 output potentially in geologic formations and thus not have the storage tank capacity requirement, but still be able to operate the Fischer-Tropsch and water gas shift reactors continuously. Also, a lower cost Fischer-Tropsch catalyst. And finally, an alternative scheme to use that CO output from the CR5s to convert to transportation fuels, but not using water gas shift or Fischer-Tropsch. We'd like to thank everyone that was helping us throughout this process and open the floor to any questions. Thank you.
Since you're removing carbon dioxide from the atmosphere, did you give any thought or for a future part of this work, running it continuously to increase your carbon credits?
So the issue is that the CR5s are the units that are consuming the carbon dioxide, and they are dependent on solar flux, so the ability to run those continuously doesn't really exist. It would be the Fischer-Tropsch reactors and the water gas shift reactors instead.
Is this designed for taking CO2 out of the atmosphere, or is it designed for taking CO2 out of the exhaust stream from a coal-fired or gas-fired power plant where you have a higher concentration? It seems that 400 parts per million is going to be very difficult to extract that.
Right, so right now this is based off of taking it from a pipeline or from co-locating with a plant. However, the dream scenario is using it from the atmosphere.
So it's part of a CCS, with that rather than putting it in the ground. Okay.
Correct.